We typically view the equation a to the n plus b to the n equals c to the n as a problem of discrete arithmetic. But within the Adelic Langlands program, these variables represent localized excitations in a series of continuous, multidimensional wave states. In logos field theory, an integer solution to this equation functions as a localized topological defect. Its presence creates an unresolvable gauge field anomaly, forcing a structural breakdown in the local metric of the field. The adele ring, denoted A sub q, maps local prime fields and the real number line into one unified coordinate system. This synthesizes discrete integers as a global lattice within a smooth continuum, smoothing transitions between p-adic noise and Archimedean infinity. To verify the stability of this geometry, we must track the behavior of a hypothetical Fermat solution. We will follow its ramification through non-Archimedean scales and observe how the global functional equation actively quenches the resulting anomaly. This demonstrates that macroscopic spacetime remains smooth and predictable because the automorphic spectrum contains no available dimensions for these pathological Diophantine contradictions to occupy. We begin by positing a counterexample, a set of integers that solves the Fermat equation for a prime exponent of 5 or higher. These integers define a Frey curve. To measure its field impact, we track two primary values, the minimal discriminant and the global conductor. The discriminant measures distortion volume. For a Frey curve, this is exponentially large, scaling with the solution's product. The global conductor, n, tracks where the curve's arithmetic breaks down across primes. In a Frey curve, this conductor is artificially small, compressing its wild ramification into only the prime 2 and the initial integers, creating an impossible mismatch against the massive discriminant. This irreconcilable divergence identifies the Frey curve not as a valid physical object, but as a fatal topological defect in the field equations. To understand why this defect cannot persist, we must evaluate it using the absolute Galois group. This group acts as the overarching arithmetic symmetry of the universe. We map the curve's n torsion points into a Galois representation, unrolling the geometric data into a 2x2 matrix format. We then project this matrix onto the Brouhat-Titz tree, the non-Archimedean space where we measure how the representation branches at individual prime scales. We focus on primes where the Frey curve experiences multiplicative reduction, localized points of constricted geometry. At these vertices, the representation collapses into a unipotent Jordan block, leaving a nilpotent shift operator exposed on the matrice's superdiagonal. This shift represents unipotent monodrory drift, a geometric scar that prevents the field from returning to its original state after a symmetry operation. By tracking this drift, the Galois representation exposes the Frey curve's underlying wild ramification at every localized scale of the tree. The next step is the execution of Ribet's level-lowering theorem. This acts as an ultraviolet filter, systematically removing high-frequency noise from the representation. The theorem analyzes the inertia subgroup, which tracks purely localized topological twists at the boundary of each prime field. Because the inertia action is weak at certain scales, the theorem systematically strips the ramified prime factors of our integers from the global conductor. This filtering proves the representation is unramified at all odd primes, leaving a global conductor of exactly 2. The filter has trapped the theoretical Fermat solution at a rigid ground state. It has moved the anomaly from a massive, complex scale to a single, verifiable baseline. The system has now prepared the defect for spectral verification, where its existence will be tested against the available wave modes of the universe. This verification depends on the modularity theorem. It states that every two-dimensional Galois representation must correspond to a global automorphic wave function. When Andrew Wiles proved this bridge, he established that an elliptic curve's geometric behavior is perfectly mirrored by the spectral behavior of a modular form. For our Fermat anomaly to exist, there must be a weight 2 modular form at level 2, a specific wave pattern that matches our conductor of n equals 2. But the automorphic spectrum reveals a terminal contradiction. At level 2, there is no such wave pattern. The space of available modular forms is identically 0. There are no physical dimensions in the spectrum for the Frey curve's wave functions to occupy. A Fermat solution would require a non-zero algebraic object to pair with a non-existent physical state. This creates an impossible spectral paradox. This paradox represents a profound symmetry break. It violates the scale inversion invariance of the universal cosmic partition function, which is required for a stable vacuum. To preserve this invariance, the global functional equation forces an active deletion of the defect. It requires the hypothetical Fermat solution to be zero. By zeroing out this amplitude, the universe quenches the unipotent drift. This prevents localized arithmetic divergences from propagating into the macroscopic field. With the anomaly removed, the continuous gamma factors at infinity can smoothly iron out the remaining arithmetic noise. This maintains the predictable, flat metric of our geometric grid. The unsolvability of Fermat's last theorem is a structural necessity for the vacuum. By mathematically forbidding these solutions, the universe prevents arithmetic chaos from warping the global metric, ensuring that emergent spacetime remains macroscopically flat and stable.